So we derived the wave equation, and we saw that, just to recap, whether it's say the displacement psi, or the pressure, or the velocity, the wave equation was same. Okay, and then where c square we derived to be gamma p naught over rho naught, which implies, in a way you can say that, okay, gamma p naught is equal to rho naught c squared. Some facts I am just summarizing so that we will use them in our present discussion. And what else did we do? I think the delta was this, and the excess, so this delta was nothing but, sort of rho excess over rho naught. Fine. So that's what we defined, and then we said that the excess pressure P excess over this P naught, which we denoted as small p, was coming out to be, say, gamma P naught delta, which you can also write as negative of rho naught c squared, you can keep it here, and d xi by dx, right. So this is what is the summary of the results which we had derived. Now using them, so what we will go to is the case where we will take up the case of, in fact that also in a way we discussed, but without mentioning the specific situation for which we wrote those equations. So you just imagine that there is an infinite, semi-infinite tube now, okay, and you have a piston, okay, and this one you are, so this side suppose is time, okay, and you are oscillating this, say sinusoidally, because these equations, what exactly do you think about them when you see these equations? They are saying that if you provide a displacement, okay, it will move, and then that could be of any shape, okay, means suppose this is a function of time, the displacement, this will just propagate at a speed of c without changing its shape and size. That is what this equation tells you. If you provide a displacement field like this, okay, and then that is where I would like to refer you to the string one. In the string, we said that if you start a displacement like this, and it just moves in this direction with the speed c without changing its shape and size, you remember? So that is where this displacement y was our dependent variable, and it used to follow exactly this equation, and that is where we were saying that this shape of displacement can propagate without changing shape and size. And now because this displacement is also following exactly the same equation, we can also again claim that analogously that this shape will move without any change of shape and size at the same speed. But then the difference being, only difference is these were transverse displacements and these are longitudinal displacements. That means you should be able to now feel how or visualize, you should try to visualize how these displacements are in the air column in the tube. Okay. So when we come here in this tube, so just think that here I have drawn a sinusoidal oscillation of the piston, but it need not be sinusoidal. Any form you give to this shape, so they will in a way, so just think about the particles which are connected to the piston. Okay, they will get the shape like this. So zeta t, or sorry, xi t is the shape you can give by displacing the piston in that form. As soon as you do that, you in a way force the particles to move in that displacement function. But and that is what is the shape I was talking about. As soon as the shape gets created, it will move at the speed c, the displacement field. So that is, this equation is telling you the displacement field will move like that. But then and it is true for any shape of this xi t. Okay. But then always we do the same thing, that for simplification we go for sinusoidal xi t to see that if we oscillate the piston in a sinusoidal way, what happens. Okay. Now, so that is what I have drawn here. So that now I am oscillating the piston here. Then we had seen earlier that the solution of that wave equation for xi would give you that, say, xi plus, I am writing because this wave is moving in the positive x direction, will be is equal to something like, say, a plus e raised to, say, I k x minus ct. Okay. Now, so you can think of this, whatever is comfortable to you can write like that. Say for example, this can be also written like a plus e raised to I kx minus omega t. So these are all the same form. Okay. Now, and again I am repeating, whenever you are seeing this complex thing, you should imagine that the actual physical quantities are real part of this. That's the convention we are taking. And and then can you correlate this with this picture now? This picture, because we are now talking that we are starting the wave by displacing the piston, we can think that everything starts with this equation. So that we can assume that this is a real number. If you think that the wave is being started by displacing the piston, that means you are giving the displacement field as the input. So you can start thinking that this is just a plus this height, and a real number, right? And then this is a cos sin omega t, cos omega t, whatever. Real part if you take, it will be cos. So the time axis will start in fact at this. So this is t equal to 0. In a way, to be consistent with this equation and this picture, I just made this. So okay, so this is how you started the oscillation of the piston. Now, if you do that, the question is what will be the pressure field downwards and what will be the velocity field downwards. Okay. Now that for that last class we just wrote down the equation, but now I'll just show you what is the meaning of that. Now see, we said that the equation of the pressure also will be of the same form, and the pressure is related to the xi like this. Okay, so we can just say that the pressure plus, I am again writing because this is the pressure field which is moving in the positive x direction. Suppose that is equal to some p plus amplitude e raised to I k x minus ct, which also you can write as in this form, whatever is comfortable to you, I k x minus omega t. Okay. Now, so here this should be complex. So now the thought process can be, it depends on your comfortness. If you think that this is your initial starting point of thought process, you can take this as real, then this will become complex in a way. If you think that you are trying to visualize in terms of moving the piston, which I am comfortable with this, because that's very intuitive to think that you are moving the piston with a given displacement function of time. Okay. Now if you do that, then now p will become a complex number, and to evaluate that in terms of this, you can simply use this expression, say d xi of dx. So d xi over dx will be nothing but p over rho naught c square, right? That was the expression. Yeah, p over rho naught c square, and so that will be what, and d xi over dx will be this is d xi over dx. P is gamma p naught delta, and delta is this, so this is d xi over dx. Okay. In fact, d xi over dt is the speed or velocity. This u is nothing but d xi over dt. Okay. So that will bring you here what? If I differentiate this, so a plus I k then e raised to I k x minus ct, right? Please tell me if I am doing anything wrong algebraically. So this should be equal to negative of this p plus over rho naught c square e raised to I k x minus ct. Is that fine? I didn't do anything, I just differentiated this, I kept it here. So now these things just go away. So your constants are now related. So I'll write p plus in terms of, what happened? I wanted to change the color. P plus is equal to I rho naught c square k a plus, right? So this is what I was talking about, that you chose a plus to be a real number, that cos actually started without any phase lag or lead to start with, okay, like this, and then you will get p with a I here, okay. So that means you're multiplying with there is a phase of pi by 2. A multiplication I means a phase of pi by 2. So now what does this tell you? It tells you that the pressure now is having a phase with the displacement which you have. The pressure wave is having a phase with respect to the displacement. Fine. Now, so that's one. Then what can we do about, say, u plus? Okay. Now, if we write the velocity field, okay, u plus will be say d xi over dt will be equal to, say, a plus, then whatever is this. So yeah, I k c, right? So this minus should be there, this minus will be coming, right, because I am differentiating with respect to time. So this I k x minus ct, is that fine? Okay. Now this is equal to your u plus e raised to I k x minus ct. So now again these things go away and you get your u plus is nothing but minus I k, something is missing, no, okay, c a plus. Fine. Now I'll just copy this expression here, p plus is, there was a minus or something, did I miss? Yeah, this minus I missed, right? You should have told me. Yeah, this is a minus. So p plus is equal to minus I k rho not c square a plus, right? So that means if you compare them, these two things, you are just seeing that u plus is nothing but p plus over rho naught c, right? And then what does this, so now we have all the expressions relating the phases or the amplitudes of all the types of waves. When I say types, means I'll just denote them now. Now this is the amplitude of xi, right? This is the amplitude of u, this is the amplitude of p. It means if you start oscillating like this, xi is a function of t, sine xi cos omega t is the function, then your displacement will be this amplitude, pressure amplitude will be this, but all will have the same form. Now this tells you that the pressure and the velocity, they are in phase. That means the velocity profile and the pressure profile, they are in phase. Okay. And this term rho c, it's a very important parameter of the medium, the density times the speed of sound in that. It is called the characteristic impedance of the medium. We will talk about that. So presently you can think that for plane wave propagation, that is when a wave that is having same direction in every location of space, so that's how we define plane wave. For plane wave propagation, the pressure and the velocity are in phase, and the ratio of pressure to velocity is a constant, the amplitudes, okay, the amplitude of the pressure to the amplitude of the velocity, that's a constant which depends only on the material property, the density times the speed of sound, and that's called the characteristic impedance of the medium. Okay. So, we will stop here for this segment and we will continue our discussion from this point onwards.